Okay, last topic that we're going to cover for today, which is kind of just this brief intro to light and optics, is polarization. So it's unfortunate that polarization is a term that's used to describe two completely different phenomena. And you must use the context in which it is brought up to help you determine which of the two a person is talking about. You're no doubt familiar with polarization as a collection of charge rearranging due to the presence of some other charge. So when charges within a body separate from each other, we say that the body has become polarized. There's negatives over here and positives over there. This is a polarized object. Here we learn about a completely distinct phenomenon that's also referred to as polarization, unfortunately. All transverse waves exhibit displacement in the direction orthogonal to their direction of motion. We know this from previous lectures. But there are infinitely many planes along which the displacement can be oriented and still be orthogonal to the direction of motion of the wave. If a wave travels along the x direction here, the transverse displacement can be along the y-axis, which I've attempted to draw in blue, and that would be in the xy plane. Or it can be in the z-axis, and that would be what I've attempted to draw in red in the xz plane, or any other axis in between. And I've attempted to draw some other axis that is diagonal. This kind of thing matters when we're talking about traveling waves. This displacement axis of a transverse wave is called polarization. This doesn't just apply to electromagnetic waves, but it's much more common to talk about the polarization of light than the polarization of a transverse wave on a string, say. Light is an electromagnetic wave composed of an oscillating electric component as well as an orthogonally oscillating magnetic component. You no doubt already learned that in physics too. Well, here we'll say that because the electric interaction of light with materials is more often of interest, the electric component of light defines its polarization. And that harkens back to what we were just talking about of how light interacts with the atoms inside of materials. It's the electric component that really does most of the interaction there. So we primarily just focus on the portion of light that's the electrical oscillating bit. The mathematics of the principle of superposition with two waves of the same polarization also extends to include the opposite polarizations as well. There are some very cool visuals online that I think show how linearly polarized waves combine. If two waves of opposite polarization are off in phase from each other, they combine to create a circularly polarized wave, or elliptically polarized, depending on the phase. And it's just very cool. So if you can find some animations of how differently polarized waves combine, two linearly polarized waves can combine to form elliptic or circular polarization, and two circularly polarized waves can combine to form linearly polarized light. Very interesting and very mesmerizing to watch. Just like white light, though, is composed of a superposition of the full spectrum of visible wavelengths, regular light is also composed of a superposition of waves in all possible polarizations. And we refer to this as unpolarized light. And so what I mean is, if we have light traveling either towards or away from you, it's oscillating up and down like this. You also have photons, right? We're not talking about a single photon, we're just talking about like a beam of light. You have some photons in there in that beam of light that are oscillating that way. You have some photons that are oscillating this way. You have some photons that are oscillating that way, and every possible way, right? So that would be unpolarized light. If it passes through a small enough slot, the unpolarized light becomes linearly polarized along the axis of the slot, because light polarized along any other axis hits the walls of the slot instead of passing through. It's very physically satisfying, and that is the way that it works. So if you have this really thin slot here, then what comes out of it on the right side is simply light that is polarized like this, because all the others, they ran into they ran into whatever material is blocking them and did not make it through the slit. One of the ways that sunglasses help to reduce the light entering your eyes in a pleasing way is by placing a polarizing filter on the lenses that rejects all the light except along one axis of polarization. And this cuts down on the intensity of the light coming through, but it also reduces reflections from horizontal surfaces like the ground or car hoods or buildings or anything else. You can read in your text how light can be polarized by reflection, but it goes something like this. So if you have some flat surface that's smooth, just like our pane of glass here, and you have light coming in that is unpolarized, right? So that means it's oscillating all different odd directions. Unpolarized light. It hits the surface here, and it ends up that the reflected light becomes polarized in such a way that it corresponds to the surface, parallel to the surface. So this happens quite frequently because there's a lot of smooth surfaces in our world now that are oftentimes horizontal, especially pavement, concrete, and like I said, car hoods and other building features. And so sunglasses, they're polarized because it only allows the vertical component to go through. So it's kind of like your sunglasses are like a vertical slit here, like this. And it rejects all these horizontal reflections and cuts down on the intensity of the light, but also rejects all these reflections, so it makes the world a little bit less hard to look at, I guess. Yeah, so this is otherwise called glare, the reflection off of horizontal surfaces. Call this glare, so it's rejecting some of those weird glare images. Some screens also have polarizing filters on them. So if you have a polarizing filter on your TV or phone or any other display, and you also have polarizing sunglasses, you can put your sunglasses sideways in front of that polarized screen and try looking at your display. What you're doing is you're putting, let's say you have a screen and then sunglasses, right? So your screen is polarized in one way, perhaps like this. Actually, it's also vertically polarized because you have to turn your glasses sideways. Just thinking about that in real time. So your screen is also vertically polarized like this. So any of the light that's coming out of the screen, it's all polarized in this up-down way, yeah? And so then, oh, never mind, it's backwards from that. It is horizontal. So, oops. It is horizontal. So coming out of your display, it's polarized like this. And so then anything coming out is going to be, did I do that wrong again? Well, one way or another, I'm going to forget it and not redraw it. But you have light coming out polarized one way, and then you put your sunglasses in front of it, usually rotated, and you have a slot like this that you're putting in front of it. And so it rejects anything that isn't polarized like this. Well, there's no light left that's polarized like that. And so what you see is complete blackness. So you can make your screen go black even though it's trying its best to emit light because you've just put two orthogonal polarizing filters in front of it. It's kind of neat. And you can also do the exact same thing with two pairs of polarized sunglasses. So very interesting stuff, worth a try. All right, so this was our very fast, brief introduction to the nature of light. We'll get more into the details of geometric optics, and there'll be plenty long, dense lectures, so I figured I'd give you a break on this introduction here. And then after that, we'll talk about physical optics and the topics and such. All right.